Absolutely.
Yeah, okay. And now I think we close that for the next speaker, who happens to be me. I have taken the liberty to change my title. I was going to ask the question whether it is possible to live on the moon, but I changed that, having looked at instead on whether it's possible to live on Earth. So my title is now a Biosphere 1 evaluation, with Biosphere 1 obviously being Earth. So I've tried to map humanity as a closed life support system, because we have exactly one data point on existing life support systems, being Earth. So the question is essentially, what do all of us do to keep you alive? And Earth is humanity's only working model of a complete material self-sufficiency and a closed system. So I tried to map 42 different materials through life, universe, and everything, using a 4-process framework to understand the global flows, and then divide everything by 8 billion people to extract the per person number. How much do we need to do per person in order to survive if we smear it out over the entire Earth? Because humanity is obviously self-sufficient, we live, but it is through an intricate world-spanning web. You can't say that you're independent of anything else. If you have a pen, it will be manufactured all over the place. This is a rather preliminary study. I intend to follow it up more carefully and make sure that statistics add up, but I thought it was interesting enough to show here. And in order to make something to present, I can't have the 42, so I divided them into groups. So we have the mine, which is making resources available. I call that mine, and that's energy extraction, taking out raw materials, resource processing, and then factory, which is making stuff, manufacturing tools, equipment, commodities. Greenhouse, which is growing things, life support, including air and water recycling there, even if that's not done in a greenhouse. Usually water recycling is a recycling plant. And then habitat, which is daily living, people doing people stuff, not just you're living at home, but also housing services, government, research, hospitals, and everything that's not part of the other three in principle. So how much land do we use for each of these? And it is, interesting enough, roughly a football field per person. And by far the majority of that is agricultural land. It's the green in the pie chart. Then there is there's forest as well, which goes into the I count that as mine, really. Built environment, habitat, factory, so that's tiny as well. So it becomes these figures. There is almost nothing that is actually used for manufacturing, as in production. Mining is pretty large if you count the entire footprint of mining where we're doing it. Well, pretty large. It's nothing compared to the plant areas. And then there is about 2 football fields of wilderness for each person. Looking into work effort, and this is assuming that you are working in 40 work hours per week, which I do, and then dividing that, assuming that all effort made into different things is equally distributed. Then I spend the first 3 days making the life of everybody else easier. Making my own life easier doesn't really come in here. And making easier, of course, includes things like tax authorities and education and research and everything that doesn't actually grow something or make something. Then the second day and a bit, the fourth day and a bit is growing stuff in the greenhouse, and 6 hours making stuff in the factory. And then I spend half an hour in the mine. So the mine is actually visible in the pie chart, but it's hardly. So interestingly, most of the things we do isn't actually producing food or producing stuff even. It's just helping each other go about our life. And extremely little on getting the resources that we need in order to do all of the rest. And producing stuff. The mine, which was half an hour, I load not just 16 tons, but it's 22 tons per week in that half hour, and the 2.5 kilowatt of energy. About 9 tons of those 22 tons becomes 9 tons of processed minerals, and then there is from the greenhouse a 1/4 ton of timber, and that becomes almost 9 tons of manufactured goods, and in the greenhouse produces 1.4 tons of food that we eat, and also in count that as factory as well, we produce about 1 new living unit per 29 years. And living unit, I mean not a complete house, but divide by the number of people who live there. So it's a living unit for 1 person. So the key insight, if you call it that, most mass comes from mining. Biological system produces food, and well, it goes through the chain. Oops, that's production. Energy requirement. I calculated that not just down to per person, but to continuous energy output. So the total energy output of the world per person is 2.5 kilowatt. Average over the year, over the day, so it's total average, of which a little bit more than 1 kilowatt is for habitat system, heating, cooling, transportation, and services connected to living and getting about. Slightly less than 1 kilowatt is factories, and about 0.5 kilowatt, well, 1/4 each for greenhouse and mining. So yeah, manufacturing and habitat are the big parts. Greenhouse and mining are quite small. So the mine, that's the source layer. Everything starts there. That's energy and resource extraction. So it's less than 30 minutes per person a week, and that gives 22 tons of materials and 2.5 kilowatt energy. And every worker, it isn't just 16 tons, it's 1,800 tons per worker and year, and 250 megawatt continuous output. Australia is highest automation and productivity in the world for mining output. And if you look at concentration risks, China has been a lot on the news lately. It's 90% of rare earth processing and 50% of coal production. Australia is leading on automating things, and Middle East produces most of the oil. So this is where everything starts. So factory, that's transformation hub. That's where everything is made. Put in the resources and you make the stuff we need. So that's 6 hours per 40-hour week. So that's only 14% of the time is spent making stuff. And the output is about 9 tons per person in year. And the productivity, I have a number saying 38 tons per worker in developed countries, which then means that this has to be a fair bit higher in the undeveloped country or the developing countries, because that's 25% and it's 14% on average. Maybe. Germany is the highest manufacturing efficiency per worker, according to statistics. And China is the highest in global manufacturing output. An interesting fact is that it's only Taiwan and South Korea who can make the most advanced semiconductor chips. I would have thought that that would have been Western countries who do the innovation, but apparently because in Taiwan and South Korea, because of the investment needed and I guess the low cost of workers. So 185 billion tons of input per year, and that's 42 billion tons of output that we use for something. Habitat, that's the end station, doesn't produce any goods. So essentially the production of the habitat, well, if we consider the output of the habitat to be more humans, we're not doing well. The world average is 2.24 children per woman. 2 would seem to be the minimum number in order to sustain population, because there are 2 parents, there need to be 2 children in order to, but then some dies before they, so 2.1 is considered to be the minimum for a replacement level. And we have a world average today of 2.24. High fertility in Africa, unless in other places. 13, 14, this is not right. And we spend, as I said, 24 hours per week doing that work. And the greenhouse, that's 1 soccer field of growing, or 1 football field. Isn't that much difference in area. If you prefer American football, that's fine too. So 26% of the work gives 5.4 tons per worker annually output, and a fifth of that is vegetables, and 80% is livestock. So the food production is much more efficient in giving production out, which I don't think I have a slide on. Yeah, I do. That's this one. So the land efficiency, there is a plant if you grow plants for eating, that's 15 to 20 million calories per hectare, while beef, it's 0.89 per hectare. So it's a factor 70 to 22 more calories for plants than per beef if you come towards growth area. And if you look at how much you use globally, livestock is 17% of calories and plants are 83% on a global level. Livestock gives larger fraction of the protein, and there are things like vitamin B and amino acids and iron that you essentially need livestock for. It is possible to do it otherwise. They are vegetarians and they are alive. One thing to consider there is that a fair bit of the livestock feed is things that we can't eat anyway. So it would make sense to have some livestock, but on a long-term lunar colony or any other place. But you can get by with much less than we do now, with probably the most efficient. Critical material dependencies. There are essential materials that you need everywhere and that aren't available everywhere. Phosphorus is only in geological deposits for fertilizer. Rare earth elements, 90% are processed in China. And actually Sweden is kind of China of Europe, because 90% of the known deposits of rare earth in Europe is in Sweden. And as I said before, advanced semiconductors, 100% are manufactured in Taiwan and South Korea. Lithium, well, that's one of the rare earth elements. It's critical for energy storage and even more limited geographical distribution. For a settlement with limited resources, you need to figure in substitution possibilities. Steel is plentiful on the moon, so that's not really important for substituting. Fossil fuels, obviously, you don't have on the moon, so that's not going to happen. On the moon, it's either it is nuclear power, which you then have to, for the foreseeable future, import a reactor from Earth, or it's renewable energy, and then it is photovoltaics or other ways to use the sunlight. And one could be to use, instead of the light as such, to use the extreme thermal differences between day and night, and employ that to drive a Stirling engine. Concrete is something that is difficult on the moon, because it contains, well, you need water to make it to start with. Partial substitution with steel, wood, or use some alternative binders. Copper is a rare thing on the moon, so fiber optics and aluminum. Fiber optics for communication, aluminum for power conduction. And one strategic priority for moon colonization, I think, is to develop alternatives with materials that can be substituted. Distribution risks. There is a concentration of critical processes which creates vulnerability. 80% of global manufacturing capacity is in Asia Pacific. 60% of food production is in just 12 countries. I don't actually know which 12. I need to look that up and include it in the paper. 90% of rare earth happening in China, which we said before. 70% of global population lives within 100 kilometers of coastline. That's not really a resource risk, but with the heating that we have, it's a risk in any way. So being able to circumvent this geographical concentration and increase complexity, then you can reduce the systemic risk from things like climate change, conflicts, and natural disaster by having a more self-sufficient, many more self-sufficient communities. So you don't, I think we are sufficiently technologically advanced now that we don't actually need to have this web of connectedness that makes it necessary to transport a car back and forth across the world several times in order to put it together. So back to the moon, scaling down. How do we do this? How do we make a small self-sufficient community, and what does it require? So I multiplied all the numbers by 1,500 to make it a 1,500 person Earth type society. So we need 30,000 square meter mine. We need a factory of 15,000 square meters. I think we have scaled this slightly for using less specialized factory here. And greenhouse 280 hectare, that's also using slightly more focused, slightly more effective production than we are currently doing. So 20 persons, full-time specialists for energy and resource extraction. 200 people for manufacturing, maintenance, and construction, 400 people for agriculture, food processing, and land management, and 880 people for services, governance, education, healthcare. You need more per capita resource allocation, and in particular, you need more people, relatively more people working with the low intensity stuff like mining and factory, and also greenhouse actually, or growing stuff, because you need to have enough people to be able to. You have to use slightly less specialized processes, which means that they are also slightly less efficient, which means that you need more people. Yeah. So technology readiness assessment, looking at what's ready today, which need development, and where research is required. I think we have most of it. We have solar panels. We can make that. It's perfectly doable today. We had wind power if we stay on Moon. We should stay on Earth. On Moon, there's no wind, obviously. Basic manufacturing, conventional agriculture, water recycling. We can get by with that. With a bit of development with advanced 3D printing, in particular for the Moon, it's closing the loop for life support, because we can't just take things from the nature and put it back out. Vertical farming, aquaculture. Research required. Yeah, it would be fine to have small-scale nuclear power, more AI, molecular recycling, nano-extraction, generation ship, but we don't really need that for self-sufficiency. So that's something, leave that for Earth. There's plenty of people on the Earth. For a lunar colony, we don't not need that kind of research. I don't know how much time do I have left? I don't even see that. That's this one. Oh yeah, there. I do have a counter. Somebody commented that the presenters should try it out. So I think that includes me. Yep, I still have time. So implementation pathways. I think phase one, we have had several talking about the implementation pathways earlier. I think phase one is to establish energy independence. That's really critical, because transporting energy is tricky. But one way to avoid that, to start up, is probably to ship a nuclear reactor. That could work. Food production, basic manufacturing and repair. Start by looking at things that wear out quickly. Build community governance and coordination systems, so people on place on site can have control over what is needed, what is running out, and what should be improved. And a few years, 1 to 3 years for that. Let's say 3 years for that, and then integration to actually close the material loops through waste recycling and reuse. And develop the specialized manufacturing capabilities to close the gaps, so that we don't need to have those chip manufacturing plants that only exist in Korea and Taiwan. And as time goes by, negotiate trade relationships with other communities, and hopefully there will be some parts of the Moon that have rare earth, and some parts obviously have volatiles, so that may be a trade relation there. And make sure that we can extract critical materials independently. Yeah. So from global web to small communities, and I think this is useful on Earth as well, but for going into space, we really need small communities that are self-sufficient, because there will not be a big community when we start. And it is a very large risk to put a community in space that is not self-sufficient, because then when money runs out, then they have to return or die, unless they're self-sufficient. So, but I think it is possible, and I think I've kind of indicated why in this presentation. So it goes from, is it possible, to are we willing to do that? Scaling advantages with going from scale advantages to flexibility and resilience, going from extreme specialization to relevant capability across all domains, just relevant, not extremely specialized. And from global trade chains to closed loop integration, from market optimization. It isn't about making sure that you get paid as much as possible. It is deliberate planning for sustainability. You can manufacture what you need. So the community question is, small-scale self-sufficiency requires efficiency losses. It requires accepting efficiency losses in low-intensity systems while maintaining essential capabilities. So are we ready for that trade-off? In space, no one can hear you recycle. Questions? And I need to check how much time I have. I don't have much time. Any questions or comments?
Oh, yeah, I wanted to comment that, yeah, this all looks like we should do this on Earth first, right? Is that?
That's kind of my conclusion as well. Yes. Why start by building a lunar colony on the moon? It's much better to do it on Earth first and try everything that could go wrong here. There will be things that can go wrong on the moon that can't go wrong on Earth, but start by trying the things that can go wrong on Earth.
Yeah.
Well, one example of that, and I've put it in the chat, phosphorus, which you showed as required for mining, and guano, the algal biomass organization has some interesting presentations on how we can recover phosphorus from sewage and use it as fertilizer.
Mm. Yeah. Yeah, the problem with recovering on the moon is that you have to start by having it, and then you have to recycle everything. But yeah, that's a good point. I think I need to break there in order to go to the next presenter. Let me see who that is.